Okay, welcome everybody to the 2020 3D printed design fall workshop. Today we're going to deep dive into the 3D printing options available to FRC teams and how to best make use of them. We're first going to look at the types of printers and printing variables, and then transition into designing with those things in mind.
Cool. Hi, my name's Anthony Diaz-Vigil. This is my 11th season, 12th season with 1678. I started as a student, went to a local college, and now I'm back as a mentor. While I was in college, I mentored also. I mainly focus on helping the mechanical sub-teams, and
And my name is Nathan McAllister. It's my fourth year on 1678. I'm a senior in high school. It's my second year as the team's design lead and third year as the robot operator.
So we'll be covering a range of topics today, starting with 3D printing technology, where it came from, how it started, why it's so popular now, the limitations of it. We'll go over a 3D printing toolkit, which is just tips and tricks, stuff you can implement into your parts, modeling tips, some variables that affect your parts, and some examples from FRC. So first off, the history of 3D printing. So 3D printing began in Japan in the 80s. It actually started with photopolymerization. So if you guys know, like, basically a MER, it's a hydrocarbon chain, and whenever you expose it to typically some energy, typically like ultraviolet light, you actually are able to break the MER groups, and they begin to reform. So when you expose a plastic, like example, a liquid resin plastic, to this light, you end up forming longer and longer chains that are solid. So that's where 3D printing initially started. That's also where the STL format gets its name. So they started with photopolymerization, and then they formalized it into stereolithography, which is where, I don't know if you guys have ever seen like a liquid resin 3D printer, but basically you're exposing whatever parts you want to solidify to high energy light, and that causes that to solidify only where you want to, and that's how you end up with your parts. During the late 80s, FDM machines were made, so that's when you think of a most common 3D printers, how they have the extruder nozzle and stuff like that, that's what those are. And then in the early 90s, people started experimenting with metal 3D printing. So there's laser sintering and there's laser melting, which are they're two very similar metal 3D printing technologies, but one involves just heating up the particles enough so that they adhere to each other, and the other involves fully liquefying them. And then the reason 3D printing has become so popular recently, as of about 10 years ago, is because the patents on FDM 3D printing expired, meaning that lots of companies kind of took a shot and started coming out with their own commercial products. So these are the most common types of 3D printing. Stereolithography, as I explained, it's where you're exposing light to MER groups in order to form a polymer. You're forming a long chain of plastic, and that's how you get your solid. Fused deposition modeling, that's the standard 3D printing most of us are accustomed to. It's where you're actually laying down material through an extruded nozzle. Selective laser sintering, you're firing a laser into, usually you have a bed of essentially fine particles of metal, and you lay down a bed of it, but just so that it's flat. And by firing a laser at certain particles, you're able to heat them up enough that they adhere to each other. And then selective laser melting, it's very similar, but you're actually fully melting the material to get it to bind to itself. Okay, so in FRC, there's a couple of printers that are actually very common. Most teams stick with FDM printers due to the advantages they have. Some teams have SLA printers, but for FRC applications, I don't think that they're as viable. Some common printers for each type. FDM printers, we love our Prusas. We have a little fleet of them. Markforged is also very common. It's a higher end machine, so it might not be affordable for all teams, but I highly recommend it. MakerBots are also popular, Ultimaker. And then in terms of SLA printers, as I said, they're not as common in FRC. So Formlabs is one of the ones I know of, but as I said, I haven't played around with them. I'm most comfortable with FDM machines. So the advantages of FDM versus SLA. There's actually a wider range of materials you can print with FDM machines. This is due to only requiring the material to be a thermal plastic, meaning when exposed to heat, the material will actually melt. Most SLA materials are thermoset plastics, meaning that once they are set, once they are solid, if they're exposed to heat, they'll burn. FDM machines are typically cheaper. They're made with simple off-the-shelf servos and stuff like that. You don't have to. They're not as research intensive to get an actual functioning machine, and typically the parts are stronger. SLA machines, they do provide higher resolution because you're not limited by the nozzle size. You're limited by the light source you're applying, so you can actually do much thinner layers. So you'll end up with a smoother surface. Additionally, FDM parts tend to be stronger because the plastics used are not as brittle as the SLA resins. Cool. So some common materials. These are for FDM machines. ABS. I'm sure everyone's played with Legos. It's a pretty standard plastic. It's got decent mechanical properties. PLA is probably the most common plastic used in 3D printing. I'll get into the reasons for that. And then nylon is another popular plastic. It's pretty tough and it's pretty good. It's pretty easy to 3D print with, but it gets a little bit stringy sometimes. So more detailed properties on them. So ABS has a long lifespan, meaning it doesn't break down very easily. It is hard, but it is not as hard as PLA. And then because of that, it's a little bit more ductile, so it's a little bit tougher. If you guys have ever played around with 3D printed parts, especially PLA, in FRC scenarios, sometimes you see them actually explode because they're brittle. If you go onto the PLA slide. So PLA is good because it's stiff, but as I said, it is brittle. One of the reasons it's so popular is because it melts very easy, which makes it very easy to print. In addition to that, when it's in its liquid state, it's a non-Newtonian liquid. So if you guys think about, like, most people have played with cornstarch and water. How if you apply a force to it, it becomes harder. Well, PLA is a non-Newtonian liquid in the other direction. So if you expose a force to a liquid PLA, it actually loses viscosity, which makes it super easy to 3D print, which is why it's probably the most common material used for 3D printing. And then nylon. Nylon is flexible, but because of it's tough, but you lose rigidity. So when 3D printing, when designing parts with it, keep that in mind. Certain printers, they take advantage of the toughness and they'll actually use nylon as the base for a composite by putting different fibers into it to gain rigidity and keep that toughness.
So 3D printing is by no means all powerful or magical. It does have its limitations. However, it does have fewer limitations than traditional fabrication on a lathe or a mill. But there are still limitations we need to keep in mind regardless. Each 3D printed part has to have a flat surface on the print bed. Most of the time, this can just be done by smart design. You need to develop the part knowing that you will be printing it and knowing that you need a large flat surface if you want it to be an easy print. If it's not possible, you can model it in two separate components. You can add a brim to the part in the 3D printing software you use, or you can raise it with a temporary structure. 3D printers are also limited in the amount of overhang they can print. So every layer needs to have something underneath it for the material to build off of. Most printers can generally print at about a 45-degree angle, but no more. And to solve this, a lot of printers will add support material underneath. And for most applications, that's really all you need. Sometimes if you want to do interior features like a zip tie path, you can't really remove the supports. So to get around this, you can pause prints manually and remove support material as long as you replace it with something to print on, or you can add a roof to your interior features so no supports are needed. So this is more about considerations when you're printing. So when filament cools after coming out of the extruder, it shrinks naturally, which means holes become smaller. And most of the time, all this means is you should oversize your holes by about 10 thou in the model, or you can just run through it with a drill after the fact. If you have critical features that you need to be perfect, though, you can try a unit test like the first picture shown. That will let you be more accurate in your hole sizing for each of the axes in the 3D printer. So the same shrinking force can cause long parts to warp during the print, causing dislocation. Some printers have heated beds or enclosures, so they don't cool as quickly, which can help with this. Sometimes all it takes is a glue stick on the bed or any adhesive on the bed to keep the part on the bed better. Another small thing to try is filleting any vertical edges on the part. Some sharp corners cause stress concentrations, and rounded corners will be more likely to stick. Another thing to keep in mind is layer shear. So parts are printed in layers, and within layers, the printer can extrude a continuous strand with a small infill direction, meaning that individual layers are relatively strong. But between layers, the printer is limited on how well it can get them to stick. So this means that the part is more likely to break along the layers than anywhere else. The majority of print failures on our team last year and the year before and all years before that were due to layer shear. So in this picture, you can see some examples. And so pretty much on the bottom left-hand corner, that picture is the first print we tried. And this part was meant to kind of hold a support tube in place for our elevator. And so you can see that the layers are going horizontally across this part. And you might now realize the problem with this because this tube is taking the force horizontally, right? And so during matches and practice, we broke this part a couple times, but then switching to the bottom right-hand corner here, that is no longer a problem because the force being applied in a real situation is going kind of against the grain this time. It's not going with the layers. It's going perpendicular to the layers, so it's less likely to break. So when you're designing a part, you need to think about where you want the layers, and obviously you need to coordinate that with some flat surface as well. Lastly, just know the limitations of your printer. Printed plastics are never going to replace aluminum and steel, but they can be helpful. So yeah, now we can switch slides.
So for the 3D printing toolkit, we're basically going to cover different features and different tricks and tips that can be implemented in 3D printing. A lot of these parts share things in common with injection molded parts, but you have less limitations while 3D printing because you don't have to worry about any flows or internal features that are impossible to mold. So the first feature that's commonly used, ribs. It's a great way to increase strength and rigidity of your part without adding very much weight. When designing the part, you just have to keep in mind which sections you want to be more rigid, and you can reinforce them manually. Lugs, typically when you have two pieces that stick together, you'll use lugs. Basically, you have the lugs that come out of the piece itself, and then you'll have two, essentially the opposite, a concave shape that's the opposite that they'll snap into. The only issue with this is the way the picture is shown right now. You'll have the lugs are meant to take shear load, so you actually have to print it in a different orientation if you wanted them to be pretty strong for high load. Next slide. Cool. So bosses. Typically they're used for features. A lot of these features can be seen if you guys have ever taken apart any injection molded parts, like a TV remote or something like that. You'll see a lot of these features in them. They're a good feature for fastening stuff. Basically, you have this cylinder with a hole in the middle so that you can actually put fasteners into it. Something else to keep in mind is if you look at the picture at the bottom left, if you just leave the part unsupported, it won't be very strong. So you'll actually have to add 2 ribs to support that part. Next slide. Oh, well, one more thing to keep in mind when you're doing this, when you're doing self-threading holes, is be sure to define your wall thickness. If your wall thickness is close to, if you don't allow sufficient wall thickness, then your threads will actually cut into it, and they're likely to separate the layers of the feature, so you end up breaking the part. Cool. So this is one of my favorite features. We implement this probably more than we should on 1678. They're insert nuts. So what we do is, because the plastic is limited, if you're threading a piece into it, and sometimes you have short pieces, you can't make a long thread for enough strength. What you do is you actually pause your print and you insert some nuts into your part. And this way you have the strength of the metal for the threads, and then the whole nut is supported by plastic all around it. So you're able to increase the thread strength when you're putting fasteners into it. So if you look at the top piece, that was a plug that went into the drum of one of our elevators. I believe it was the 2017 robot. And basically, the drum was a giant cylinder as a piece of pipe. And what we did was we made this plug. It goes into the end of the pipe. And then if you look at the sorry, I can't point. If you look at the top right picture, if you see those square features, we actually slid nuts all the way into them, and then we had holes that came out radially. And in the pipe, we drilled and we put bolts through so that you can actually transfer a high amount of torque. I believe on the other end, it's not shown here, of this plug, there was a pulley. So we're actually able to support our whole elevator and transfer power to it through a 3D printed part. Cool. Some other things that are useful. Zip tie paths. A lot of 3D printed parts require fixturing stuff or holding things in place. So we actually really do like our zip tie paths. If you look at the picture at the top right, we have it's for our solenoid manifold. And basically, because of how we're mounting stuff, we have these zip tie paths that secured our manifold into place properly. Additional features that we rarely use this one, but snap fits, they could be useful for making other enclosed fixtures for different parts. The only thing I will say is they take a little bit of trial and error, so a little bit of trial and error to figure out how they work. Especially in 3D printing, because 3D printed parts they have different strengths in different directions. So if you're trying to implement these, make sure that you actually have several test parts that you try before actually putting them into the part, and make sure that because it's a flexing part, make sure that the layers are perpendicular to the way it bends. Otherwise, you'll snap the piece off. Some other things we've done in the past, actually this is very useful, part fixtures. If you have 3D printers in your shop, but you only have a manual mill and you need to do some complicated angles or something like that, then you can actually print a fixture for the part. And you clamp onto that fixture and it'll hold your part at a fixed angle. So you can mill whatever features you want. This is also really useful for doing like large batches of parts. If you have like a ton of a certain part you need to do, You just drop your parts in, machine them real fast. They're always fixed in the same place so that you can produce multiple parts accurately and quickly. And then finally, molded parts. I've seen before a lot of COTS parts were available, especially like soft rubber wheels, teams would actually 3D print mold for wheels and stuff like that, and they'd cast whatever rubbers they wanted. If you can't find like a wheel or something off the shelf that meets the criteria you want, this is a good route to go.
All right, so we're getting into some actual modeling tips now. And normally this is not like the most ideal thing to talk about in a presentation, but some 3D printed features, with some 3D printed features, figuring out how to model them is quite a challenge sometimes. So it's really important to model resiliently. When parts are this complicated, you need some level of organization for features. So one of these things we do to ensure resilient modeling is this guideline, this top right picture. Modeling a part resiliently means you can go back and edit it at any time, and the main structure of the part stays the same. It models things in logical order to maximize your efficiency. It can really be applied to anything. For example, if we take a look at these gearbox plates, you can see it starts with a master sketch where all the critical dimensions, center to centers, all of that is laid out. This is a really easy thing to do because you can go back into the sketch, edit at any time. All the bearing holes will, switch places, and you'll have no issues. Everything will just fall into place after it. Next, you want to model the core features. So things you actually care about, like how you want the part to function. At this stage, the plates are just rectangles with holes. They're very simple, but they can still be put in an assembly to verify it works. You can also get feedback. You don't have to worry about pocketing, which is kind of a time suck, especially if you have to go back and edit the pocketing. That is probably the most annoying thing you could possibly be wasting your time on. So finally, after you've got confirmation that everything works in the assembly, figured out any conflicts, you can model out the details. So pocketing, fillets, mirrors, all of that good stuff. By saving the details for the end, you don't have to repeat them over and over again, like a lot of us try and do. And you don't have to worry about the sketches referencing small details like fillets if you do them after. And that can become really annoying when you accidentally reference something like a fillet, and maybe you go back and delete it and everything turns red and you're mad, and you just want to punch your screen. Not the best thing in the world. So although this example is with plates, the same ideas apply to 3D printing parts. Just really important to kind of make sure you're being organized and deliberate with how you kind of organize your features here. So some of the best ways to model resiliently are using multi-body parts. So in SolidWorks, this is a lesser used feature, but in Onshape is kind of built off of this idea. So model the material in need, floating in space, and join them. This could ensure that the material will always be there and is unlikely to break. Makes it easier to mock up a part and develop it later. And it forces you to think about the function of every piece of material. That being said, sometimes this approach is not necessary, and all it does is add complexity. Multibody parts or part modeling is also ideal for interconnected parts. Without them, you would have to model each part separately and then put them together in assembly, which is known as bottom-up design. You need to constantly reference the other parts to make sure they'll fit together, and if you want to change them down the line, you have to make changes to all the parts. The idea of top-down design simplifies this workflow. As I said, Onshape is kind of built around this idea, and SolidWorks has the capability, but it is quite limiting. This is great for making mounts for other parts or moving parts. You'll waste a lot less time back and forth between part and assembly if you do this top-down design. So this slide is getting a bit more specific into the features you might want to use in modeling 3D printed parts. When it comes to modeling parts, there are certain key modeling functions that are used differently or not at all in other areas of FRC design. The shell feature is a good way to reduce material in printed parts. It's just one step to quickly make a very complicated part or very complicated cut in your part to lighten it up, much faster than trying to pocket parts manually. The loft feature is also one that I don't think I've ever used outside of making a 3D printed part. It just creates a smooth feature that connects two profiles, which is a super easy solution to a 3D printed part. And lastly, the filleting is commonly used in FRC, but when it comes to 3D printing, you can truly fillet anything you want. A simple fillet can greatly increase the strength of a joint on a 3D printed part. It's really easy to go through and fillet all the interior angles in a printed part, and it will make it stronger. So I definitely recommend doing that.
All right, there's several variables that are taken into account when you're 3D printing. One of probably the most important one that will affect your parts is the layer height. So most 3D printing softwares, they'll give you a couple options for the layer height. Either you can do a fast print, which will have a thicker layer height, or a thin print. Thin prints have a nicer surface finish because you're actually you're smushing the plastic together and you have much higher resolution. Whereas thick prints print faster. The main problem with thick prints is that because if you think of the extruder as extruding a circle profile, because you have two circles laying on top of each other, you actually end up with stress amplifiers between the layers, and the layer adhesion zone is already the weakest part of the print. So you're actually introducing stress amplifiers into the weakest part, which makes it even weaker. I would not say that your part is that fast printing is useless, because although you are losing your layer adhesion strength, you're actually gaining some strength because you're keeping the extruded plastic profile more intact. You're not having to squish it as you do when you do thin layers. So you do lose layer adhesion strength, but you do gain some strength in the opposite direction of your layers, in the direction of your fibers. There's some other things to take into account. Wall thickness, this one's very important also. Typically, whenever you print a part, the wall thickness will give you, like, if you guys think of a box, if you guys had like some sort of plastic box and it's open without a lid, then it's very easy to bend it. But as soon as you create that closed surface, you end up with a lot more strength. So because of this, whenever you're making a part, even if your infill is light, you want your wall thickness to be fairly thick. Especially, you want your wall thickness to be fairly thick, especially when you're not limited by thin features. Like sometimes you might be limited by a gear tooth or something like that, or a part has to be fit into somewhere. But if you can afford it, make the walls as thick as possible for the most strength. And then also, while doing that, keep in mind that I know a lot of software takes this into account, but if not, keep the wall thickness as a multiple of your extruder nozzle diameter. Otherwise, you end up with some funky stuff where you're kind of printing into another layer of material, and then it just doesn't bind as nicely. And then infill is also another important factor. Typically, I think most printers for default settings, they print around 30% infill, which is the material inside of your part. This makes it so that you don't have to use as much material while printing your part. It saves you money, but it also makes your part lighter. The only thing that can be an issue is if you don't provide enough infill, your parts will be a lot weaker. And then when you're determining your infill, it's not a linear strength relationship. Once you get up to about 50% infill material, then you start seeing a lot of diminishing returns with your 3D printed parts. So keep that in mind. Typically, you don't go up to 100% just because you get a lot more diminishing returns the higher the infill percent gets. And then there's several infill patterns. These are some of the basic two-dimensional ones, but there are more advanced three-dimensional ones. Rectangular pattern, it's very quick to print because everything's a straight line. It's also pretty strong, I would say. The only thing is it is stronger in one direction than the other. You're actually stronger when you're going with the direction that the crosses are. Triangular prints, typically whenever we're printing pulleys or anything like that, we like to go with the triangular setup because it's not as directionally determined. The strength is not as determined by the direction of the triangles. It tends to be a pretty uniform strength in all directions. So if you're printing a pulley or something like that and you want all the teeth to be strong, typically I'd go with triangular. And then honeycomb. Honeycomb provides some of the advantages of triangular. You can kind of think of it as if you're to take out the center sections of the triangle. So it actually ends up being pretty strong, and it can be lighter than triangular. The only thing I'll say is that with some printers, when you make a honeycomb pattern, it takes a little bit longer than if you were to do a square pattern print, just because the printer has to change directions much more. Same with the triangular. With the triangular prints, because as you can see, all the lines are continuous, you're actually able to print those pretty quick as opposed to the hexagonal pattern.
All right, and this slide is more specific to the higher end printers like the Markforged. If you're careful about how you do it, adding thin layers of reinforcement material can really increase the strength of your part. So common materials are carbon fiber, fiberglass, and Kevlar. On 1678, we have a Mark II printer with carbon fiber as the additional reinforcement material. I will say, though, that we rarely use it. The Onyx 1 and the Mark II are mostly just used with Markforged stock Onyx material. Rarely, like maybe once a season, do we have a part that needs this reinforcement material, the carbon fiber reinforcement. So there are two general kinds of reinforcement. The concentric reinforcement adds rings of material around and outside the print, which increases the wall strength and hole strength of your part, while layer reinforcement stiffens the part from flexing perpendicularly to the layers. You can define the angle you want the print to extrude at, giving it extra strength in certain directions. For maximum efficiency, you can add sandwich panels to your print. When a load is applied to one end of the part, most of the forces are at the top and bottom of the part. So by adding thin layers at the top and bottom, you maximize the effectiveness of the reinforcement. So now we're going to move more into how to successfully design for 3D printing, kind of where you should be using 3D printing on your robots. These are places where 3D printing really offers an outstanding solution. So the first application here is fast iteration on complex designs. 3D printing will never be able to work as quickly as a couple of mechanical kids with some plywood and hand drills when it comes to simple prototyping, but there are times when you need complicated parts in your mechanisms that need to be iterated quickly. So the perfect opportunity for this is using a 3D printer. You can print most parts overnight, no matter the complexity. So these pulleys right here offer a great example. These were complicated parts that needed to be changed quickly to make our robot climb. It would have taken forever to remake these on a lathe. So instead, we could test one size, then maybe print a new size overnight and just test again the next day. So 3D printing for prototypes should not be overlooked, especially when you want to iterate fast. Electrical sensors and mounts are also two of the most common applications of 3D printing in FRC. There are a few good reasons to develop printed parts for your electronics. You can group several similar components, such as pneumatic manifold, solenoids together for simplicity. It frees up belly pan space, which gives your team more room for mechanism. mechanisms and reduces your constraints. Lastly, it also makes the electrical team's life much easier because the components can be assembled ahead of time and quickly just fixed onto the belly pan. Electrical mounts are also a great thing to develop during the off season because you can reuse them year after year. You don't have to spend time on them during build season when your time is everything. Sensor mounts are also a great application of 3D printing. The places that sensors are needed on robots are often the hardest to reach. And so when these mounts need to be rigid, accurate, and reach awkward places, 3D printing can meet all of these requirements with smart design. A great example is with mag encoders. So 3D printed parts are always accurate, usually lighter than aluminum, and can be designed strong. You'll see West Coast products using 3D printed mag encoder mounts for their swerve drive, or before they switch to Falcons. But that's just one example of how you can use mag encoders. So printing pulleys is another solution that 3D printers can be used for. Obviously, you don't want to be putting these pulleys in super high torque situations. They offer lighter, or they are lighter than the aluminum pulleys. But large pulleys, for example, is kind of the best place to use them because there is less load on individual teeth and no hex profile. So you can also use them for dead axle plugs, like Anthony was talking about. You can, well, rather than having a move-in shaft mounted to a plate through bearings, dead axle is a stationary shaft that rotates around the part, or that your part rotates around. So they can be as simple as a pulley with bearings in it. These dead axle parts have several advantages over live shaft systems. The dead axle shafts can act on a standoff and can help support plates. They're much stronger. They allow you to define the method of power transmission rather than relying on hex profile for power transmission. And for long high load applications, this can be necessary. Dead axles also have multiple moving parts around them at different speeds. So that might be helpful if you're trying to transmit power through a shaft in two different places for two different mechanisms. Dead axles are not specific to 3D printed parts, but 3D printed parts make it easier to, I guess, produce solutions and kind of worth the complexity there. So again, this last slide is more specific to high-end printers. It is a common problem in FRC to have tubes joined at an awkward angle. So solutions to this include bent gussets and aluminum blocks, which are both hard to get right at points, especially when you have them coming off diagonally like we did in 2018. So this is an application that 3D printers can be really good at. So those have been kind of the areas that I see having the most potential in FRC. Feel free to take those suggestions or not. Obviously, we are not full experts by any means. We are still learning, but I encourage your team to kind of explore the options here and figure out what works best for you. So now we can move on to questions if there are any. The Citrus Circuits email is also, or the hardware email for Citrus Circuits is also up here, and I will get back to you as soon as possible there if you have any questions after the fact.
Yeah, we still have time for questions right now. So if you guys have any questions related to 3D printing, robot design, I don't know, anything we covered in this Onshape, feel free to ask. Cool. If not, thank you for attending our presentation. Hopefully next year we'll be able to have an actual in-person competition and more presentations for you guys.